Welcome back to another video by Firestarter Graphics and Engineering. I'm Matt Thomas. Today we're going to be going over the paper that I wrote for IEEE for the IREC 2023 Renewable Energy Conference. Wow, that's a lot to say. Okay, so you can read what the title is. It's a pretty lengthy title. This is for Utah Valley University, and this is the wind turbine. Actually, this is kind of the baby brother of the wind turbine. We're dealing with 5 megawatt utility sized, so 65 meter length blades and 90 meters high. So roughly 3 feet to a meter, so 270 feet tall and about a 200 foot length blade. That's what we're dealing with. So we're going to be doing the prediction of fatigue and life using a few open source pieces of software. So let's kind of go over the outline. We're going to have an introduction, obviously, and then talk about the methodology and experiments and the metrics that we used for all of our testing. Then we'll move into the simulation using OpenFast, which is one of the software packages, and the static loading analysis that we did. And then move into the analysis using MLife, which is another open source software which takes the data from OpenFast to calculate fatigue. And then we'll talk about things like how blade pitch affects power generation, lift, drag, fatigue, and how even the blade pitch can affect the lifetime of the blade. And then we'll move into conclusions and then do the acknowledgements. So, kind of a slight introduction. Over the last 10 years, there's been a huge growth in advancing wind technologies, and the National Renewable Energy Laboratory, or NREL, they have produced some great software, and 3 of those packages is TurbSim, which is a turbulent wind simulator. It generates wind files for you to use in OpenFast, which is a really awesome simulation tool that calculates a lot of things. You feed it inputs. For example, there's like 2,000 different inputs you can give it, and it will spit out the outputs of those things. For example, in our files we have 52 inputs that we want it to calculate. Wind velocity in X, Y, and Z direction, the forces in the X and Y direction, the moments in X and Y directions, the max loading, the tip deflection, in plane, out of plane tip deflection, tons of different things. And you use MATLAB or another program called PyDatView, a Python library, to view those results. And then what you do is you take MLife, which is a MATLAB program, and feed it all the data from OpenFast, and it will calculate fatigue and life and something called DEL, which is the damage equivalent load. So, the way to get started is to quit talking and begin doing. Great quote. So let's quit talking and let's actually do something. So the methodology that we used is what we call an iterative scrum method, where we gather data, put into static analysis, and then use that static analysis to give that information to OpenFast along with input and initial parameters, which goes into OpenFast, and that data goes into MLife, and then we start all over. So it's a wash, rinse, repeat, over and over and over and over. So we did about 200 to 300 different tests. So you gather the data, everything you want to do, change the initial parameters, change the inputs, and then put it back into OpenFast, and then just keep going. The static analysis we only did once, because that's really not changing too much. But the data from OpenFast, the reason why we did 200 to 300 different tests is because we changed a lot of initial parameters in there, like the way the wind turbine behaves and the wind speeds, the pitch angles, and so forth. Okay, so with that said, the objectives, we are focused on the aspect of monitoring and analyzing loads on a Dutch offshore wind energy committee 65 blade. It's a lot to say. That is abbreviated as DOWEC. The blade is made up of NACA 64 airfoils from the National Advisory Committee for Aeronautics, and totals in length of about 62.9 meters, but we're just going to call it 63 for the heck of it. The application of fatigue analysis is instrumental in averting premature structural failures and damage. So when you evaluate the stress levels and load cycles and cyclic loading, this can help you accurately produce reasonable results of durability and longevity of the turbine itself. So kind of a lot going on. But the beauty of it is this is the blade, and when we put it in ANSYS, based off the information from OpenFast and our hand calculations, between all three there was only a 7% error. So I think we did pretty good. Okay, so first I wanted to look at the airfoil equations that are used for NACA 4-digit series. And the reason why I want to do this, I want to get an accurate surface area so that we could plug it into ANSYS, OpenFast, and the static analysis to get better second moment of equations, to get better, more accurate results. So, using a chord length of 4.3 meters, and then a thickness, which is the height. So 10% thickness was used for this purple one, which means it was 0.43 meters, and then a 7% thickness here. And then you can see this empty area. That is the surface area we wanted to compute. So we integrated each function and then subtracted it and ended up with 0.6 meters squared. And that includes the symmetry as if we were to complete and mirror these airfoils underneath. So speaking of static analysis, this involves assessing the behavior of static components when subject to forces and loads. While it doesn't account for dynamic effects or extreme conditions, it is highly effective in evaluating the structural soundness of wind turbine blades under typical operating circumstances. So using the basics of a cantilever beam, these parameters and these input parameters right here, these are the most important ones that we used for the static analysis. Distributed load, we used 840 kilonewtons because the normal operating conditions of these wind turbines can handle between 800 and 1,000 kilonewtons, so we picked 840. That number is actually important of how we picked that number. One of our first tests from OpenFast, we got a max loading on the blade of 444. So then when we multiplied it by our safety factor, we got 666, added in the weight, and that gave us 840. So we figured, let's keep our baseline at 840 kilonewtons and then work from there to see what happens. So using our cross-sectional area from the airfoil design, a Young's modulus for fiberglass, and the length, we're able to find all our reactions and the deflection of our beam, which was about 9 meters. And this distributed load is nothing more than just the area of a triangle. 840 is equal to base times height divided by 2. So you can fill in the information you need and figure it out from there. So with that in mind, our baseline, like we said, we wanted something that was going to be kind of our control. So we picked a really high wind speed, 12.2 meters per second. As you notice, in the United States, there's nothing that gets that high. The highest is 9 meters per second here in the central side of the United States. But the average is about 5 meters per second. So 12.2 was perfect. If we could determine baseline factors at 12.2 meters per second, then it would be much easier to figure out things at a lower wind speed. This graph right here is the file of our wind speed generated by TurbSim. And you can see how it just fluctuates so much. That's what I like about the turbulent simulator. It's not just a straight line of constant wind. It's more realistic of turbulent wind. And it lasted for about half an hour, which means about 75,000 timestamps. So lots of data in OpenFast just in that single half an hour. Okay, so initial conditions, we left everything 0 except the rotational speed. That was fixed for every single test to be 12.1 RPM. So we just, for our control, everything else was 0. We'll change certain things here in a bit. So each test I said was 1800 seconds or 30 minutes. This allows the system to reach steady state so that all the fluctuations and transient response are leveled out. So this is an actual screenshot of OpenFast and what we had set. Okay, now this is what we call the theoretical steady state conditions. So there's a lot of automatic sensors and a lot of controllers inside of a wind turbine that change the pitch angle of the blade automatically depending on the wind speed to keep max power generation and efficiency. So this is part of the NREL design guide, which is page 32, figure 9-1. So you can see from 0 on the red line, 0 to about 11.5 meters per second, the blade pitch stays 0. And then about 11.5 it starts climbing. And you'll notice, see, these are the transit responses. It's still trying to get that torque generation up. And then it starts leveling out right here. So let's look at like 18 meters per second wind. We'll have a 15-degree pitch angle, but a constant torque. So it means our power generation is constant and probably most likely max power generation. However, when we tested at 20 meters per second, we got an instant fail because of a tower strike, because there's so much deflection in that turbine blade that it hit the tower. So that's why we stuck with 12.2. So 12.5, just for kicks and giggles, we're roughly 5-6 degrees, is what we should theoretically be picking for that wind speed to get max power generation. But let's find out if that's what really happens. So here's our numerical results for steady state. So as you can see, with our constant wind speed and our varying pitch degrees, actually your pitch angles in degrees, you can see how power generation stayed at 4.55. The max loading stayed pretty similar, and the damage equivalent load, which we'll go over here in a minute of what this means, and then the time to failure is 20 years. What's interesting though is we hit 13 degrees. So let's go back one. So where's 13 degrees here? Is roughly 16.5 meters per second, but we're using 12.5 and we're using 13 degrees. So we're way off from the chart. But yet with our results, it's interesting that we get 21 years and we get 4.55 megawatts. Pretty easy going on the max loading, and our damage equivalent load is low. So we hit about 20 degrees, everything's good. Then 25 we start dropping. We drop a little bit in power. Dang it, didn't mean to click, sorry. And then if we look right here at 27 degrees, we get a great time to failure, 33 years. This looks promising, but we're only generating 177 watts of power, very little power. So this means the blade is starting to stall. Then we hit 45 degrees and our loading just increases. So 657 times our factor of safety. I mean, we're pretty high, and we only get 10 years of life, which is interesting. Bad conditions, you still get 10 years on that blade. That's pretty cool, but no power generation. So graphs on the side, you can see wind compared to blade pitch angle compared to power generation. So 750 seconds, when that wind dips way down, we get very little power generation, about 1.5 megawatts. But right here, when we get max about 5 megawatts, our blade pitch is about, it goes from 7 all the way up to almost 12. And you can see how the wind is. So you can just see how things automatically kind of change themselves based on, they simulate the sensors in OpenFast. Okay, so let's look at this. Now we're using the theoretical steady state. So 0, 0, 0, 13 degrees, and 12 meters per second, because we're basing it off these graphs now. and power generation is great. Time to failure is 21 years, but 30 years for this one. But the max power is not too bad, 3.23. So you could potentially, at 10 meter per second winds, if you can find a place that has that, you'd get this much power generation for 30 years. So you might be cheaper than getting better power generation but a lower time. However, 6 meters per second, we get an infinite life. It's like 75 to 100 years, and only not even a megawatt, so not too great. And so most failures actually occur with corrosion in the studs that hook the blade to the rotor. It's the root hub. Those blades corrode and the vibrations damage the epoxy resin inside the blade. And bird strikes don't help. Some of those big birds out there get hit and it damages the blade. So, and like I said, at 20 meters per second it fails instantly. So kind of interesting to see how the pitch and the wind speed, how it affects loading, power, and damage equivalent load, and its fatigue. So this is just a graph that directly shows how the drag is increased with your increasing angle of attack and how lift is decreasing, eventually till you get a stall, which is right about here. Okay, so this graph shows the direct correlation between blade loading and lifetime. So 50 years with a blade loading of about 175. For us, we're about 389, so we get 20 years. So easy going graph. Alright, so to assess the fatigue life of a wind turbine blade, several trials using OpenFast provided detailed time series data. Remember I said about 75,000 timestamps. And that's all for the dynamic forces acting on the structure. Then we take that and MLife extracts that information from OpenFast and subjects it to rainflow cycle counting to identify stress cycles and amplitudes. And then MLife converts that cyclic force into a single output known as the damage equivalent load. So you have this wave pattern, the cyclic force. So imagine the blade just moving up and down, up and down, up and down. So it does that a certain amount of times until it fails. And if you take all of that force and put it into one single concentrated point load, that is your damage equivalent load. Which this is calculated by dividing the ultimate design load by the safety factor, and our safety factor is 1.5. So let's look at those MLife results. So we have 806, but then you're asking, wait, I thought you said 840 kilonewtons. That is true. When we used 840, we had a 15-year lifespan. We were aiming for 20 years, so naturally that would go down to 806. So we have 806 kilonewtons in the X direction, then we have 980 in the Y, then you have your moments, and everything was calculated to be 20 years plus a little change in the decimals, but it was all rounded down to 20 years. So, but as we changed the wind speed, like I said, to 4 to 8 meters per second, an estimated infant operational life of 100 years. So conclusions. The main scope of the study was to computationally calculate fatigue and longevity of the wind turbine. We used OpenFast to do so, and then ran multiple tests, like I said, 2 to 300. Gave all that simulation data to MLife, and then it did its thing, and we were able to generate all those pretty graphs and then give this awesome presentation. So with that said, thank you, and we're grateful for the support that we have by the Utah Systems of Higher Education. And we're grateful for the efforts of OpenFast, the contributors of OpenFast, and all the authors of the software. They have been indispensable in playing a key role in this presented research, and we're very grateful for it, and we're grateful for this opportunity to present at this conference in Africa and to have our paper published by IEEE. This is great, and we're very excited. So thank you for watching, and God bless, and happy holidays.